Hello, everybody, and welcome to day 3 of PyData Global. We're super excited to have you here today for this session. A little bit of housekeeping for this particular session. This is a 90-minute session, and during that time, the speaker has asked that we sort of hold our questions till the end, if that's at all possible. In order to do that, during this session, you can feel free to chat and connect with fellow people in the session by using the chat tab. If you have any questions that you'd like to ask, you can put those in the Q&A tab, and we will moderate those towards the end of the session when Joe's ready to go with that. So with that now, it's my absolute pleasure to introduce you to Joe Pringle, and they will be presenting a talk on computer vision, data version control, and reproducibility at scale. An exciting session we've all been looking forward to. With that, let's give a warm virtual welcome to Joe, and you're on stage. Take it away.
Awesome. All right, Arliss, thank you so much for that introduction, and thanks everybody for joining. Good morning, good afternoon, good evening, wherever you might be. I'm excited about today's topic on computer vision, data version control, and reproducibility. And my name is Joe Pringle, and I am the VP of Customer Success at LakeFS. And I thought I'd just tell you a little bit about myself before I talk through the agenda and what we're going to do in this session. Just to give you a sense on how did I end up in this space of data version control. So currently I'm at LakeFS and I lead our customer success efforts. But I spent my entire career working with organizations of all shapes and sizes on how do they leverage their data to work smarter, make better decisions, be more efficient, and be more impactful in different ways. And I started out in consulting for about 10 years or so, doing data and technology consulting. I then shifted over and worked for a couple data and analytics platform companies for 8 years or so. And then I spent about 6.5 years prior to LakeFS at AWS, where I was an AI and data strategist. And my job was to help large, complicated organizations figure out how do they build capabilities with AI, and how do they leverage and use their own data to support those AI capabilities in different ways. And my focus has also been on highly regulated industries and how do we use AI on high stakes use cases where the cost of a mistake is high or the risk of failure is high. And for some reason, that's just been the part of AI that's interested me the most. And you know, it's one thing to use AI if you're creating a TikTok video, or if you're writing advertising copy, or if you're coming up with like a recipe for your holiday party. But it's entirely different thing to use AI for healthcare or finance or government use cases, where if like literally if your AI system makes a mistake, people can get hurt or people can die in some situations, and there's just a lot of repercussions, and so that creates a much higher bar to build AI capabilities and systems that are reliable and trustworthy and safe to use and accurate and auditable. And so that was really my focus at AWS, and I gradually sort of had this realization that, and actually it wasn't just me, it's like I think everyone is sort of realizing currently that there's this broad class of generalizable models that we can use for everyday sort of speech and language chatbot types of tasks. But then for lots of other use cases, those models aren't good enough. They make too many mistakes. They're not reliable enough. And there's been lots of excitement about agents. Well, in my work at AWS, like agents are not ready for a lot of the really high stakes use cases that I tend to focus on, and it's because they make mistakes, and we can't make them reliable enough. And so the answer increasingly is we need to use our own first-party data. If I'm a company, if I'm a government agency, I have to use my own data to build a smarter, better, faster model that really is reliable and trustworthy on a very specific task. Or I need to build a model or a system that understands not just how to engage in a conversation, but it understands the physical world. And it understands, in the case of, let's take autonomous driving, what does it mean when I see these objects in a scene? Like, that's a really high stakes question to ask an AI system to help with. And so all of that's leading up to, I sort of had this realization that the hardest thing that most of the customers I've worked with have to deal with is dealing with their own data and managing their own data as they build these systems. So that was a long sort of monologue about my journey of like how I ended up focused on data version control. But that's just a little bit of context. So let's talk about today's session. So I want to start with giving you an overview of what is data version control and why should I care about it? How does it work? I want to start with a little bit of a foundation, and then we'll spend the bulk of the time actually getting started, getting a little bit hands-on. First, setting up a data version control environment with LakeFS and some other tools, and then going through an example of how we would use data version control in practice when we're actually building a model. In this case, we're going to build a computer vision model. So that's a little bit of an overview of the session. And I did ask to maybe take questions at the end. I'm not quite talented enough to operate this, this Airstream and the demo and take questions. So I think I would mess up. So, but I promise, I've saved plenty of time for discussion at the end. Okay, so let's start with what is LakeFS? What is data version control? And I think the best way to understand what it is to talk about our customers and what are they trying to do. And there's some example customers on this slide, and they're all very different. There's Fortune 500 companies from lots of different industries. There's government agencies. There's research organizations. There's startups. There's companies that are building their own models. There's customers that are using models that other people built. But they do have certain things in common. One is they tend to work with large-scale data, often object store data that they're using for building models or using models in a different way. And they do lots of iteration. Sometimes they have a very high velocity of data. Their data is changing all the time, or they're doing lots and lots of experimentation and iteration, and they need to do that efficiently. They also have sometimes distributed teams where different teams play different roles in the life cycle of data, from when it's captured and managed and stored to when it's processed for machine learning and prepped to when it's actually used to build a model or when it's used for inference. There's lots of reliability concerns that our customers have. Again, I mentioned I've kind of have this background focused on highly regulated industries, high stakes use cases. This is the same with many of our customers, where they need AI systems and models that are trustworthy and reliable and also reproducible, and in some cases auditable. So that's a little bit about why LakeFS exists and why people use data version control. A good way to view us is we sort of fit in the middle of a typical data AI stack. And on the top of this slide, you have a bunch of different data AI tools that data engineering teams or ML ops teams or data scientists might use to build and manage and deploy AI systems. And at the bottom, you have object storage. Most of our customers have some object store data. Many are very large scale, and they're using data lakes and things like that. And this slide makes it kind of look sort of simple, but the reality is object stores and data lakes can get very messy and complicated. And the reason is, part of the idea of data lakes is we want to make it easy to ingest data. We don't enforce some sort of schema or validation for someone to publish data into a data lake often. And this is great. It makes it easy to capture and store data, but then that imposes a tax. When we then want to access those data to do something with it later, that makes it harder for us. And so one of the problems we see over and over again is a lot of times our customers are the data engineering teams, the data science or ML ops teams, and the tools they use, the stack they use, it always has an imperfect understanding of that data layer, that object storage layer, because things are moving so fast and things are messy down there. I'm sure many of you have heard the term, data swamp, and it's sort of a cliche, but it's true. It's really hard to manage a data lake over time and prevent this from happening. And so that's what we focus on, trying to provide this layer that sits in between the data and AI toolbox and the data itself, to make it easier to utilize data and build the kinds of AI and data systems that our customers are trying to do. We also hear about sort of specific pain points that different teams or different individuals experience when we have this like data swamp phenomenon. One is around discovering data. And you take a large distributed organization that creates lots of data, and data is changing and different teams are working with data. It's really easy to have this like defensive copying sprawl phenomenon where lots of different teams use lots of different data, and then a given team, when they need to go find something, they're having to do a lot of like data archaeology just to figure out what is the right version of a data set that I should use. What is sometimes I have to wait a long time to get data provisioned for me in an environment, and a team might say, hey, we want to use production data, but to safely experiment, we actually need to copy all this data and provision it for me to do some experimentation on. That takes lots of time. And then it just perpetuates this data sprawl phenomenon. There's also lots of collaboration challenges where when you have like a lot of the customers we work with, they have really complicated data and data pipelines, where I mentioned this autonomous driving as an example. Well, in a lot of cases, there's lots and lots of data prep, data processing work that needs to happen before a machine learning team can actually do anything. For example, if you take an autonomous vehicle, it's got a gazillion different sensors on it that are capturing all sorts of data. There's LiDAR data, there's radar data, there's telemetry data, there's sensor data, there's video. And often what data engineering teams need to do is they need to stitch all that data together. And sometimes we're using some of the data to describe other data. So we're sort of combining data in these hybrid complex formats. And so that there's a lot of complexity there. There's also a lot of steps and teams involved, and it's easy for different teams to step on each other's toes. And if one team makes a mistake, it can cause a lot of rework. So that's another thing we hear all the time. Third is anybody who's working in AI these days, we know GPUs are scarce and they're expensive. And so we have lots of customers that spend a lot of time and effort figuring out how do we optimize the GPUs we have. Maybe we have our own on-premise compute where we have GPUs and we want to keep those GPUs as utilized as possible so we don't have to buy more really, really expensive GPUs. Or in the case of cloud GPUs, sometimes we can scale up and scale down, but often we need to rent GPUs 24/7. And so that's, again, same idea. We want to keep those GPUs utilized. And so we have a lot of teams that what they're trying to do is, one, they're trying to recover faster from data pipeline failures, where if a pipeline fails on step 22, maybe we don't need to go back all the way to step 1. We can go back to step 21 and we can complete that pipeline faster so we can start our training job faster and we don't keep the GPU waiting. Or there's other cases where actually delivering the data to the GPU is like the rate limiting step. And so being able to deliver that data faster and orchestrate that better is a huge cost saver, or it's really an efficiency. It's an efficiency thing. And then lastly, we have customers that, either, I mean, most of our customers need to be able to reproduce experiments and internally say, hey, which team built this model 6 months ago? How did you build it? What data did you use? That can be a hard question if you aren't using the right tools for that. And that's part of what I'm going to show in my my demo and workshop. We have other customers. This is actually a legal requirement. They have to document exactly what data was used, and they need to be able to go reproduce that data in the exact state that the model was trained on. So that's just some things we hear from our customers, just some themes about why data version control is useful. And it turns out, like, for a lot of these problems, we can sort of take a page out of a the book for software engineering, where for decades we've used Git, uh, and I'm not a software engineer. I'm going to out myself a little bit, but the same concepts, the same operations we can apply to manage code and manage pretty complex multi-person or team interactions around versioning complex code bases. We can do the same thing for data. We can use branching to experiment safely, to collaborate and allow people to sort of make changes to data in a way that we can then keep track of and manage. We can merge changes in an orchestrated way back into a main data set or repo that we're using as sort of our golden data set, for example. We can enforce validation and prevent the wrong things from getting into that data. Right now, for example, GDPR or HIPAA are huge requirements that most of my customers deal with, and they need to prevent the wrong data, PII in particular, from being used improperly in their models. And not only that, they need to be able to prove that they didn't use PII when they're training a model. And then lastly, we can create snapshots. We can use commits and tags to take a snapshot of data so that we can then recreate that exact state of data that we want to use 6 months later or a year later. So that's a little bit about how data version control helps with this. And now I'm going to sort of kind of tie it to object storage. So if a good way to think about object storage, it's just a collection of buckets that contain objects, unstructured files, or they can be structured, but it's the beauty of object storage is we can store anything. And this slide kind of represents a bucket with some objects in it. And the thing about applying version control to object storage is the data can get very, very large, terabytes or petabyte scale data. And so what we don't want to do is we don't want to copy data when we need to experiment. So there's this ability to create zero copy branches. And the key to this is these are metadata operations. And so if we have a repo of data, and here's the data we want to use on March 25th, what we're doing is we're describing the exact metadata of the objects in the object store. And then as time passes, we might delete some objects and maybe we add some objects. And now we can do another metadata operation of that same data, that same bucket or same data lake. And now we can say, hey, here's now what we're using in this repo. And under the hood, we're not copying objects for that second commit. Or if we create a branch, what we're doing is we're doing a metadata operation. So this lets us do this kind of data version control at this scale of data in a way that's performant. And so that's a little bit about what is data version control all about? Why is it important? And now let's get started with the workshop. So what I want to do first is walk you through how to set up a data version control environment powered by LakeFS on your local environment, or if you're working in a cloud environment, this works for that too. So if you go to this link, or if you use this little QR code, I'll leave it up there for a second, or you can just Google LakeFS samples. Oh, I should say this is kind of a cooking show workshop. I'm going to sort of point you in the right direction. I'm going to show you resources as I go. I'm not going to try to complete every step in this 90 minutes because we're doing more stuff than that would allow. And so I don't think you're going to be able to follow step by step, but I'm going to try to kind of describe exactly how I'm doing everything, and then you're going to be able to replicate this on your own. All right, so when there is a getting started section of this LakeFS samples, if you scroll down, that walks you through how to spin up an environment. What it does is it creates several containers, a notebook server that I'll show you, a MinIO S3 compatible object store. We could easily use AWS or GCP or Azure or some other S3 object store if you want to, and then an instance of LakeFS. So that's what it does. I'm also installing MLflow, and I'm going to use that for experiment tracking for this. So now I'm going to just flip over into just kind of show you this stuff here. So here's LakeFS samples, and there's just tons of stuff here that I would encourage you to check out. There's a bunch of sample notebooks, including, I'm going to point you to in just a second, the notebooks that I've modeled this workshop on. There's also a bunch of standalone examples where if you want to access how to use LakeFS and data version control in conjunction with lots of other tools that many of you are probably using. The world is your oyster here, and there's lots of examples here. If there's something that isn't here, let us know. We're always adding stuff to this. I mentioned here there is a kind of a getting started guide. There's also a tutorial in our documentation. If you go to LakeFS documentation, there's sort of a step-by-step tutorial that helps you follow along and also practice sort of basics of how do you set up LakeFS and do different things. So let's, again, cooking show style. So I've set up LakeFS using that process. And what I'm going to do now is just show you the basics. This is sort of what the UI of LakeFS looks like. In the actual walkthrough of building the model, we're going to do this programmatically, but just to kind of help you visualize what we can do in LakeFS, it's sort of what you can imagine. We're going to do some basic things where I'm not going to use this repo, but I'm creating a repository right now, and we're going to load some data into it. So here I'm just doing that in the UI, and let's say I'm, this is my main branch. Often we want to start with a kind of our initial data in main that we're using, and then what we're going to show these Git-like operations on how do we do data version control with data, and we can create tags and say maybe this is our raw data, and we can create a branch where this is part of the idea of data version control is we can create a branch from main so we can safely experiment on main. And this happens really fast. Like, this is teeny data, so it doesn't matter. But if this were like terabyte, petabyte scale data with either lots and lots and tens of thousands of objects or large files, like creating this branch is really fast because it's a metadata operation. We can make changes to this branch now. We can safely experiment without breaking the production data set. So let's say I'm going to do some experimentation. Maybe I'm changing the data that I'm using to train this model, and I'm deleting some files, and I'm going to add some files. So now I have an experiment branch that is different from my main branch. So I've and then I just committed those changes. So now my experiment branch differs from main. I can actually compare, just like I can with Git and code. I can show these changes. I deleted some objects, I added some objects, and now I can merge that, or I can do a pull request and manage the changes to main. If I realize, like, hey, these changes are what I want to be reflected in my production data. So let's merge that, and let's actually add some metadata to that. So we're describing, I'm not going to do it right now, but we'll do that in the workshop. So this is part number one in this setup, is this LakeFS environment. Part two is what I'm using for my object store, in this case on my Mac, is MinIO. So this is S3 compatible, and I just, when I was interacting with LakeFS, I was actually interacting with this bucket under the hood. I created a repo. I created this this path in this bucket, and the data I was loading, it shows up here. So there's this relationship between LakeFS and sort of the underlying object storage that you're using. The notebook server looks like this, and it has those sample notebooks in here. And I'm going to call, actually, there's a little index. So there's lots of stuff you can use to kind of get started with LakeFS. I would encourage you to check these out. And there is a couple of notebooks in here called ML Reproducibility and ML Experimentation that I modeled today's workshop on. I did make some changes. I couldn't resist. I wanted to sort of tailor today's session a little bit and make certain points, but you'll basically be able to follow along a very similar example if you use this ML Reproducibility notebook. And then lastly, I mentioned I set up ML Flow. So I'm going to use ML Flow in the session to show you how do we actually track the models that we create and the model experiments that we do, and use that alongside with LakeFS to show you the data that we're using throughout that process. So that's kind of the toolbox that we're setting up in this session. And now let me describe this example that I'm going to walk you through, and then hopefully you all will be able to sort of replicate this on your side. So what I'm going to use as a scenario for this is a healthcare AI scenario, where let's imagine we're building a computer vision model that helps us detect what's called diabetic retinopathy, or DR. And what we want to use is some images of normal retinas and some images of diseased retinas. And we want to see different ways we can train a model that can use, maybe let's imagine we want to create like an early screening tool for this diseased retina, diabetic retinopathy. And I'm going to use this kind of as an excuse to show data version control and how it sort of manifests itself in a typical end-to-end workflow for building a model. And I'm going to also point out some of the reasons for using data version control, and kind of in the process of building the model, but also in being able to kind of reproduce or audit or document the model after the fact. I kind of went through the toolbox that I'm going to use. Here's a few more details. I'm not going to read all this out, but I am going to take a sip of my Gatorade here. All right, so let's jump into it. And now what I'm going to do actually is flip over to VS Code. And I am using VS Code because, and apologies for scrolling. I know it's kind of hard to watch someone sort of manipulate a notebook in a situation like this. So I'm gonna kind of explain what's going on here for each cell that I execute. I'm using VS Code because I can use my GPUs on my Mac easier than that Jupyter container that I showed you. It's the same idea though. It's just going to be faster for the things I'm doing here, so you don't have to wait on me to train models and stuff like that. So all right, so let me do just a few little logistics cells here. I'm going to load some libraries here, ignore those error messages, and I'm going to configure a few things. And I have just sort of configured my LakeFS environment, my MLflow environment. I've specified what repo I'm going to use. I'm going to now connect to that. So here's my LakeFS environment. Here is the repo that we're going to use for this. And we're starting with a single branch that has these I showed that example of the retinas. So this has data on retina scans that have this DR condition and some that don't. And so that's what we're going to use here. And oops, sorry about that. And I'm going to set up a few little helper functions that allow me to kind of interact with LakeFS in different ways. And now I'm going to load data. And so what I'm doing here is I'm actually loading data into my local Mac environment from that main branch. So, and this could be, maybe I'm using some sort of cloud infrastructure, cloud GPU instance or something like that to do data processing, or so just kind of use your imagination based on the kinds of data processing you do. I'm just sort of replicating that for the purposes of this demo. And now let's take a look at the actual images that I just loaded. So here is what they look like. And at the top here, we have normal retinas. And then in the bottom, we have retinas that have this disease. And our goal again is to create a model that can spot patterns in these pixels to make this prediction of does this scan have this condition, yes or no? That's our goal. All right, so here's a little bit about the data we have. I should maybe I'll caveat a few things. One is this is kind of a simulation. I'm not building this model for real. I'm using a really small sample of data, so everything kind of trains fast. It actually introduces a little bit of variability in how these models are going to perform. That's good because I actually don't quite know what the outcome is going to be. And second is I'm not a professional data scientist. I've worked with lots of really talented PhD data scientists, and so I've learned some things by osmosis over the years. So that I use when I'm doing things like this. But you'll see any of you who are real data scientists in the room, you might see some things that you disagree with. So I'll just apologize in advance for that. So I'm defining this architecture of the model that I'm going to build. And I'm not going to go through in detail kind of what we're using here. We're using this model and for defining some parameters that we're going to train with. And I'm going to use the same architecture for each training run that I do. So the first thing I'm going to do is I'm going to use that baseline data and I'm going to train a baseline model. So, and thanks to the fact I'm not using a whole lot of data here, it trains relatively fast. And let's see how well this first sort of baseline model performs in hopefully just a second here. All right, so I'm going to scroll up and we can take a look at this here. So here's our model, and so we had this 200 samples for our validation set, and we have what in this sort of simulation, let's imagine what we care most about is false negatives. We want this to be a sort of a rapid screening tool where we're catching if someone has this condition, we want to send them for follow-up tests that are more accurate or whatever, but we want to do rapid screening. So let's just imagine this is what we care the most about. Of course, we care for false positives about this too, because that means we need to send somebody for a test that doesn't need it. But let's just say we care most about these false negatives. So this is our baseline model. So what I'm going to do now is I'm going to log some things. And first thing I'm going to do is I'm going to actually write some metadata here that, again, this is simulated, but in the real world of healthcare AI, there's lots of metadata requirements. So where did this data come from? How did we capture it? So we have like data on the populations where the images were taken. We have data on the actual imaging equipment. We have other things that we care about. So when we evaluate this model or we want to recreate this model, we can use this later. So we'll hold that thought. There's a lot of metadata we need to deal with. Now what I'm going to do is I'm going to log this first baseline model to MLflow. And so so we're just logging this experiment. There's a few little error messages popping up here that you can safely ignore. And now I'm going to, so what we just did there is we logged this experiment. We can go look at that in just a second, but I also want to commit this model metadata to LakeFS. And I'll explain why in just a second. So I'm doing this commit where I'm actually capturing some of the MLflow model architecture metadata in LakeFS, and I'll explain why that's a useful thing. And now this is our baseline model. We're not super happy with it, but it's the model we have, so we're going to deploy this model to production. All right, so now let's flip over and just kind of take a look at what did we just do. So again, I mentioned we were sort of working off of main, this kind of baseline model, and in MLflow, we did an experiment. And this is the baseline model we just changed. And when we look at this model in MLflow, sorry, that's a little small, we can see certain things about the model performance. We can see this metadata I created, I logged it into MLflow. So this later, when we need to sort of audit this model or reproduce this model, we know a lot about how this data was created for the model. We also know model performance parameters and lots of things about the model architecture, et cetera. We also have a link to the exact data that was used to train this model. So not only do we have the metadata about the data, but we have this immutable link to the actual data that was used. And so that's super important. So we can go back and we can retrain this model on the exact same data that was used. Even if that object store has changed, we can use the snapshot of this repository. And then if we go over to LakeFS, we can see this MLflow metadata here in LakeFS. And so there's sort of this bidirectional linkage between our machine learning experiment tracking and our data version control. So we can, if we're looking at it from the ML experiment side, we can figure out what data was used. If we're looking at the data, we can figure out what experiments were run with this particular snapshot. So that's step one. So we just created and kind of did some logging of our baseline model. Now let's say that we are, someone has realized, hey, Joe's not a very good data scientist, and we can do better, which is not surprising. And so we're gonna train a new model. In this case, I'm gonna keep the model architecture the same, but I'm gonna change the data. And so the first thing I'm gonna do is I'm gonna create a branch. So I'm creating that 0 copy branch of the production data so I don't break anything and change that data and mess somebody else up. And then I'm going to make some changes to that data. So what I'm going to do here is I'm going to augment this data set, and I'm going to actually sort of make changes by creating simulated data. And so I'm rotating some of these retina scans. I'm shifting them a little bit. I'm zooming in. I'm flipping them around, and so then I'm going to now kind of run this little data processing job, and then I'm going to load those augmented images onto this branch on LakeFS. So let's say maybe I did a much larger scale data processing job and, on the cloud. Now I'm logging those, I'm loading those into this LakeFS branch, and I'm going to make a little commit of what I just did here. So let's look at that briefly. So now if I go to my repo and I look at my branches, I now have this new branch, and I have this new data that I've added to this. That isn't on main. I've done this, I've done this safely, but I have my new data that I'm going to use that's going to help me train this model. All right. So now let's do that. Let's train the model on this data, and let's hope for the best here. So, I'm sampling from this augmented data, and my hope is by doing this technique, somehow I've sort of created a better training data set, as anybody that works in this space would know. Okay, so here's my V2 model, and as I had hoped, I did actually do a little better on this critical metric. My performance of my model is a little better. Still very much amateur grade, but it's progress. So we've reduced the amount of false negatives, which is what we care most about. So let's log this model to MLflow. Which takes annoyingly long for some reason. Okay, and then let's log this information to the LakeFS repo. So once again, I'm gonna flip over here, and let's just take a look at MLflow. And I'm gonna look at my experiments here. And now I have this new experiment that I did, and same metadata that I'm capturing, but I now am using a different data set to train this model. So the only thing that's different here is this change. So if I want to recreate it, this is what I need for that. And then I can link over to this branch on LakeFS, and I can see the ML experiment metadata at the same time. And again, I know it seems like we're doing a lot of logging here, and in a little bit, I'm going to sort of like, sometimes if you're just working on your own and you're building models locally and you're a team of one, like, this stuff isn't nearly as important. It's when it's like large scale distributed teams, lots and lots of different models, when you need to go figure out what someone else did, their good work, like doing this sort of thing, this is what makes your job much easier. Sometimes if you're like me, if you forget what you did yesterday or last week, like, it's also helpful in that case too. Okay, so let's say, okay, we're okay with this. It improved the model a little bit, but we're going to try one more thing. And so I'm now going to do a different experiment where I change the data in a different way. So I'm actually going to create a different branch, and I'm going to use a processing technique that is called CLAHI. I'm sure I'm pronouncing it wrong, but it's contrast limited adaptive histogram equalization. And I'll show you what this does. Really what it does is it increases the contrast of the pixels we care most about in these images. So this is used a lot in kind of healthcare diagnostic imagery types of things. So we're gonna create a branch and say, okay, we're gonna try something else. We don't know if it's going to work, so we need to safely experiment. So I'm going to create this new branch. I'll click on it, and so now we've cloned once again, we've cloned this from main, and now I'm going to apply this data processing, and it goes through and it sort of processes this on 1,000 images, and now I want to sort of show what it did. So here is what CLAHI does. It's like, these are the regular images, both sort of a mix of diseased and normal ones. And what it does is it increases the contrast of the structures that we want the model to pick out. So in theory, this should do better than the other models we built. So I'm going to load this model to this second experiment branch. We're calling this experiment improvements. So I'm loading that up. And wait for it. Now I'm going to commit that. And so I just created a little commit to my repo for this branch. And now I'm going to train a model on this. And again, same architecture. Same number of samples. And let's see if this technique helps us at all. Okay, absolutely not. Actually, it helped us on the wrong thing. So now we're doing really well on false positives, but we've done worse on false negatives for some reason. So this is the nature of machine learning. You never know what's going to work until you try. So now, but let's log this. So we did this experiment. We're going to log it. Maybe somebody else is going to do some Klahi data work in the future. So we're going to log the experiment to MLflow. And we're going to log the MLflow data into my LakeFS repo. And now let's compare the models that we built. So, excuse me. So here's our different models. We have this baseline model, we have augmented data, and then we have this Klahi model. And in some areas, the Klahi model performed better, which is great. But the most important thing, it actually performed way worse. It performed even worse than baseline. And so maybe we huddle as a team and we realize, hey, the augmentation model is better enough that we're actually going to promote that model to production. And so now what I'm going to do is I'm going to actually merge this data to production. I created those experiment branches. I'm going to say, hey, we now have a better production model. Now our current golden training data for this model is now from this augmentation experiment branch. And I'm also going to promote the model to production in MLflow. Okay. So now let's just kind of go back and look at everything we did here. And again, like if you're working by yourself locally or building your own models or whatever, the benefits of all this work don't necessarily, they're not as important. But if later, like let's imagine 6 months passed and the team has changed and some new data scientist has come on board and their job is to say, hey, we fired Joe and now we have a real data science team and we're gonna build some much better models. And that team can now go back in and look at these experiments and understand exactly how they were built with this detailed metadata. This is exactly what MLflow is all about. But crucially, what we've added to sort of a standard way to use MLflow is this ability to go back to the exact state of the training data that we used. And so we can go back over to LakeFS and we can now see here is the detailed metadata of how the augmentation experiment that we've merged into main. We can look at and sort of recreate and understand in particular, how was this data changed? Actually, this is my model documentation. Let me go back. But we can see how did Joe create this data? And what did he do to create this specific snapshot of the repo? Because maybe he's like a total crap data scientist, but he did a decent job. Somehow he got lucky and he created like a really good starting point for my next experiment or something like that. So that is like, to me, that's some of the benefit of, why if you put a little bit of time into this approach, this saves, I don't know, we've heard, customers talk about saving, 5 to, in some cases, 10 hours a week for their ML practitioner team, because they spend so much time recreating or finding data that was used for particular things. And so the payoffs, it takes a little bit of an investment, but the payoffs are significant. Okay, so let's go back over here. And now let's imagine that we are, we're doing a healthcare AI product, and we're saying, hey, we want to submit this for FDA approval. In the US, the FDA regulates healthcare AI. In the EU, there's the medical device regulation. And so there's requirements that we need to meet to get those AI capabilities approved. And a lot of those requirements are documentation. We need to document how these models were built. We need to be able to show a third party how to reproduce those models. So I'm going to create a sort of a simulated document. Let's imagine this is like, there's a lot of paperwork here. You have to submit, like, here is this system that we built, and here is an overview of it. But the really hard stuff, if we hadn't been doing all this hard work and capturing this information, it would be really, really hard to compile this information that we need to be able to show exactly how we built this augmented model. So I'm going to sort of scroll down here, and maybe we could have information about the model performance, and here's how it performed and why we think it's deserves approval or consideration or whatever. But what we're pulling out of MLflow and LakeFS is all this metadata that we were logging for these experiments. So there's like detailed information about the model and the model architecture and the training process, where a regulator wants to see, like, exactly how did you build this model, so we can audit it or we can replicate it, so we don't think you're making this up. And even like the training infrastructure. But then if we keep going down, sorry for all the scrolling, eventually we get down to the data where it's like, hey, yeah, we can show all this model metadata, but we can't, if that object store, if I'm operating in a data swamp, I can't replicate this model because I can't replicate the training data that was used. So, but what I can do, thanks to all our diligent logging and tracking, I can see the exact data commit that was used for training this model. And I can replicate this repo, this state of this repo when this snapshot was taken exactly. And so that is the benefit of, for a lot of the customers we work with, that's kind of shows in a very simulated, contrived example, like, how do we actually use data version control to support what we're trying to do. Okay, so now I'm going to flip back over into presentation mode for just a minute. And let's just wrap up a little bit with one. If you missed that link earlier, here's the samples for spinning up the environment I used for that walkthrough I just did, and all the those notebooks that I modeled my example on. You can find them all here. Grab this QR code, grab this link. If for some reason you don't get it or whatever, you can always follow up. Also, join our community. We have lots of open source users of LakeFS, and they are there's lots of smart people in the community working on all aspects of this. So take advantage of that as well. And with that, I wanted to just kind of open it up for questions or discussion.
Hey, Joe, that was great. Thank you very much for doing that. Yeah, at this time, I don't see anything in chat or in the Q&A. but I'm sure we'll give folks maybe a minute there and they'll think of something. So.
If you don't want to ask it now, and if you have questions or anything you want to ask later, here's my email. Feel free just to reach out if you want to. And yeah, I would love to just hear what you folks are working on, or if there's a specific project or problem that anybody has that we want to talk about here or later. It's all good either way. All right, Arliss, I'm not seeing anything from the group. I hope that was useful for everybody and you got something out of the session today. And I really appreciate everybody joining. Have an awesome day.
Great. Thank you, Joe. As I said, appreciate it greatly. So thanks, everyone. We're going to end the session now. Enjoy the rest of your day. Take care.